And maybe I should start off by saying really what I'm going to talk about is the role of thermal densities on instabilities in the magnetosphere. I think these slides are completely the wrong way around. What I've illustrated here is the growth rates and the resonant energies for electromagnetic instabilities between waves and particles in the radiation belts. And the only point I want to emphasize on this slide, well, there are 2 points I'd like to emphasize. First of all, that for electromagnetic instabilities, the resonant energies scale proportional to the magnetic energy per particle, b squared over 8 pi n, and therefore the plasma density is going to come in terms of the scaling of this energy. It's going to be important because we know that the spectrum of radiation belt particles falls off quite rapidly with increasing energy, and therefore, to a certain extent, high-density plasma regions will lower the resonant energies and therefore produce a more viable instability. But you can't make the densities too large because you notice that the growth rates themselves scale in proportional to the number of resonant particles divided by the total plasma density. So if you make the plasma density too large, you're going to reduce the growth rates. Oh, wrong way. Now what I've illustrated here is the value of b squared over 8 pi n, typically through an equatorial cross-section through the radiation belts. And you notice that it has a steep increase at the plasma pores, of course, where the density can decrease by a couple of orders of magnitude. Now, if you had a detached region out in the outer plasmasphere region, the resonant energies in this region would also be very low, probably in the order of 10 keV or so. Now, these qualitative concepts which would indicate that by increasing the plasma density, you would decrease the resonant energies and therefore bring the main bulk of the plasma into unstable resonance with the waves, have been put on a more quantitative footing by Cooperman and co-workers. And I show something published in the last JGR in which they show here the growth rates for a plasma with a beta of a tenth, pitch angle anisotropy of a half. And what they've done is they've parameterized the growth rates as a function of the ratio between the hot and cold plasma densities. 15 here would, for instance, indicate that the cold plasma density is 15 times the hot density. And what you can see is that for this particular set of conditions, the role of increasing the cold plasma density is to both increase the range in K-space over which the instabilities occur and also increase the growth rates themselves. Now, last year at the Chapman Memorial Conference, Coroniti put quite a considerable damper on a theory which he, Cornwall, and myself had published about 2 or 3 years ago, in which we were talking about the instability of ring current protons during storm periods. What we had initially contemplated was that during a storm, ring current protons with energies, say, between 10 and 100 keV would be injected into the night side of the magnetosphere. On gradient drifting around towards the day side, they would tend to intersect the plasma pores, and at the time, we thought that the outer zone region itself would be relatively stable. We now know that is not correct, but I still believe that instabilities along the plasma pores region can exist, and I'll try to show you an example where I think this is occurring. During the recovery phase, one also expects the role of the plasma pores to come into play, because we do know that the plasma densities will gradually increase in the region which was initially, which was during the storm period, depleted of cold plasma density. And we had suggested at that time that this increase in the plasma density as the plasma pores moves back out could be a possible mechanism for the excitation of sour arcs. Well, what Coroniti, Fredericks, and White have shown in a paper published approximately a year ago is that the outer zone itself can become unstable. It can become unstable to both an ion loss cone, electrostatic ion loss cone wave, and a high beta ion cyclotron electromagnetic wave. And if you plot the regions over which the instability can occur in parallel and perpendicular velocity space, you see that it covers nearly the entire region. So one would expect, indeed, the particles injected with very large anisotropies into the outer zone to be unstable to these instabilities. But once the anisotropies have been relaxed by the ensuing instabilities, one would expect the region outside of the plasma pores to become relatively stable. And it's then only possible to remove the ring current protons either by charge exchange or by ion cyclotron instability inside the plasma pores itself, because the electrostatic instability doesn't work in regions where the density is high. Now here's some data taken from the ESRO-1A satellite during a storm period. The onset of the storm was approximately here. You notice that this is precipitating protons in the energy range of 100 to 200 keV or so. You notice that in general, before the storm period, one finds precipitating protons primarily in the region larger than 60 degrees invariant latitude. But during the storm itself, namely, this should typically be outside of the plasma pores, but during the storm itself, the precipitation moves into very low L values, and then gradually, and also intensifies, of course. Now, I've taken one satellite pass from the main phase of this storm, or two satellite passes from the main phase of the storm. This data was given to me by Finsaurus. And here we plot both the precipitated protons with energies between 100 and 200 keV and the trapped protons measured at the ESRO-1 satellite altitude. And you notice here that the entire outer zone, all the way from L of 3 out to the outer boundary of trapping, presumably, is subject to strong pitch angle scattering. The trap flux is approximately the same as the precipitation flux. Between 3 and 3.5, however, the precipitation flux undergoes a very pronounced drop, 3 orders of magnitude or so, whereas the trap flux just falls off smoothly. This is the inner edge of the outer zone. But then there is a further region of very intense, strong diffusion loss on L shells just inside L equals 3. And I would like to tentatively, although there's no proof of this, associate this with the ion cyclotron instability occurring within the plasmasphere, whereas the outer zone losses here are probably a combination of the high beta ion cyclotron instability together with the electrostatic loss cone instability. In further support of this, one orbit later, the region which was initially devoid of intense precipitating flux on this orbit, this is only an hour and a half later, suddenly shows a very pronounced precipitation flux. And I would interpret this as an outward motion of the plasma pores during the 1.5 hour period between these two orbits. And as the plasma pores moves out, the protons become eroded, and you dump out the protons now which are within the plasmasphere. Well, what one should probably look for, because the main phase of the storm can be very strongly controlled by the source injection events, but during the recovery phase of the storm, the picture should be more easy to understand, and we have proposed, Cornwall, Coroniti, and myself, that during the recovery phase of the storm, strong ion cyclotron turbulence should be generated just within the plasma pores. This can then undergo Landau resonance with the thermal electrons of a few eV energy, and this would tend to heat up the electrons, and the heat could be conducted down towards the ionosphere to produce a red arc. Now, I presume that Dr. Rees will discuss the production of red arcs in more detail, so I'm going to skip on and not go into these details. Another interesting thing is that one could begin to look at what would happen to the electrons due to similar instabilities between Whistler mode waves at the plasma pores interface. Now, what one observes typically throughout the entire plasmasphere is a His band, which has been termed plasmaspheric His. It's a right-hand polarized electromagnetic wave with frequencies typically on the order of a few hundred hertz and a bandwidth also a few hundred hertz. And what I've shown here is the variability of the amplitude of the 550 hertz channel of such wave emissions observed on the Ergo 6 satellite during a storm period. Here again was the onset of a magnetic storm. Now, the interesting thing is that during the main phase of the storm, there is a pronounced reduction, if anything, of the plasmaspheric His emissions. One finds very little intensity at all, and this is probably very close to the threshold background value. But as soon as the recovery phase of the storm begins, presumably when the plasma pore starts to move back out into the outer radiation belts and therefore begins to move into the region where the electrons have been injected, one finds a very pronounced intensification of waves in the 550 hertz channels, and in fact it occurs over the entire band. And this enhancement of the wave energy can extend for several days after the storm period. Now, we've also looked at substorm. Well, this just gives us statistics of this enhancement of the plasmaspheric His emissions during the recovery phase of the storm. We just plot the probability of seeing a certain amplitude wave as a function of quiet times, storm main phase, and initial phase, and the recovery phase. And you see the most intense emissions are observed in the recovery phase. Now, during substorms, we again use the OGO 6 satellite search coil magnetometer. And what I've plotted here is, again, the amplitude of the 550 Hertz channel on 4 orbits during a substorm period. Now, before, I'm taking data from this period here, which is a relatively isolated substorm, which is preceded by quite a quiet period. And I've blown up this section. This is an hourly AE. I've blown up this section of the substorm period by plotting 2.5-minute averages of AE. And what one observes on a satellite orbit which moves from dawn to dusk and then across the pole is, before the substorm period, quite intense emissions in the dust sector, essentially nothing to speak of in the dawn sector. But at the onset of the substorm period, one finds that the intensity in the dust sector is greatly diminished. And on this orbit, you can see there's absolutely no emission at all in the dust sector. But at the same time, the emissions at dawn are strongly intensified. Now, we interpret the emissions which are seen in the dawn sector primarily as chorus emissions. Both, I don't want to go into the method of identifying it because it's not too easy. But it's primarily as a function of which L value you see the emissions at, and also the frequency characteristics of the spectrum of the wave. But the thing I want to point out is that following the substorm period, the emissions at dusk come back again, and the emissions at dawn go away. Now, one can understand this in the following very simple model, that prior to the substorm, electrons are essentially, if the electron energies which are giving rise to the emissions, say, have energies on the order of 10 or 20 keV, one would expect them to be subject primarily to gradient drifts and circles around the Earth, essentially. But during the substorm period itself, you switch on the convection electric field, and you bring in plasma sheet electrons which drift around past the alphane point and then drift off towards the magnetopores. Now, we can understand the reduction of what I would interpret as His emissions in the dust sector as a function of this changing orbit of the particles during the intense substorm period, when the convection electric fields would carry any particles on the day side off towards the magnetopores boundary. And similarly, as soon as you switch off these electric fields, any particles which had been injected and producing rather intense chorus emissions over here, they would begin now to drift off into the bulge region of the plasma pores and possibly give rise to the His emissions which are seen. Well, let me now turn to some aspects of detached plasma regions. This is a typical example taken from the Lockheed light ion mass spectrometer. You can see a well-defined plasma pores, and then as you move further out in the magnetosphere, you find a very structured region with densities rising from the normal trough densities between 1 and 10 particles per cc up to densities approaching 80 or so. Now, one would expect that such detached plasma regions should be associated with enhanced wave turbulence. And here is an example of what one sees during a transit through a detached region of the search coil magnetometer data. And one finds that in the 100 Hertz channel, a very pronounced enhancement of the emissions, which seem to model very well the enhancements, even the fine structure of the enhancements in the plasma density. Now, I hope that Jacqueline Etcheto will say something about this, because she has been working on a theory which is directly relevant to the emission of such waves in detached regions. Here is another example, a well-defined plasma pores position, and again a detached region which is associated with a pronounced enhancement of the wave emissions in the frequency range between 200 and 400 Hertz. Now, also at much lower frequencies, PC1 band and I guess PC3 band or so, one does observe waves which could be associated. The 5-second waves here could probably be associated with ion cyclotron waves, and these would be much longer period, of course, PC3 waves. But these do seem to be be enhanced during transits of detached plasma regions. Now, one can begin to speculate what would you expect to see, both by measuring precipitating particles on the ground, for instance, and also by looking at changes, say, in the pitch angle distribution of particles as satellites traverse such detached plasma regions. And one of the things which I'd like to bring to your attention is that if you do have, say, an injection of protons into the night side of the magnetosphere during a substorm period, these protons, once they're injected, could produce emissions, well, both electrostatic ion cyclotron waves and electrostatic loss cone waves and high beta ion cyclotron waves in the region outside the plasma pores, presumably also electromagnetic ion cyclotron waves in the region just within the plasma pores boundary. And if these protons have enough anisotropy, by the time they reach the dayside region and they can encounter a detached plasma region, you would expect to find ion cyclotron turbulence within such a region, or at least associated with it, together with possible Whistler mode waves due to electrons which are also injected during the substorm, drifting around, of course, the other way. Now, it turns out the ion cyclotron waves are particularly interesting because not only do they resonate with protons of energies, say, ranging from 20 or 30 keV on up, but they will also resonate with relativistic electrons. And if you put in typical numbers, you find that the scattering of electrons by, say, only 1 gamma PC1 waves, which is quite a modest amplitude to be observed in this region of the magnetosphere, you find that such scattering can take the particles onto strong diffusion, and you would expect to find very strong precipitation events into the atmosphere. Now let me show you one last slide, which indicates that probably some of the events which have been identified as REP, relativistic electron precipitation events, by Bailey and his group in Alaska, and also by the Scandinavian VLF forward scatter, VLF forward scatter link between Aldra and Tromsø, could possibly be associated with the ion cyclotron turbulence in detached plasma regions and located just within the plasma pores boundary itself, respectively. Now, what happened is a substorm occurred soon after 1800 UT, and more or less immediately with the onset of the substorm, the phase of the signal a phase of VLF signals transmitted between Aldra and Tromsø showed a pronounced decrease, and the phase decreased to below the threshold, to below the daytime reflection level, which is indicated by the dashed line here. Now, even before the substorm, there was a significant phase anomaly, because normally during nighttime conditions, when this was taken in the Scandinavian sector, the phase should lie roughly along the dashed line here. But in order to advance the phase to below the daytime level, you require electrons to penetrate to below 70 kilometers, and for that you roughly require MeV electrons. So one can interpret this phase anomaly of the signals as a precipitation of relativistic electrons into the atmosphere above the Scandinavian sector. Now, roughly 3/4 of an hour later, the forward scatter link between Barrow and Anchorage at 23.2 megahertz began to show very anomalous absorption, rising to about 18 dBs. And one can interpret this again only in terms of the precipitation of very energetic electrons, possibly with energies exceeding 400 to 500 keV. And this time delay can be explained in terms of the drifting time of protons injected into the night side magnetosphere, drifting around through the plasma pores region, generating turbulence which could possibly give rise to the precipitation of electrons over the Scandinavian sector. And then approximately 3/4 of an hour later, the protons would encounter a detached region above the Alaskan sector and give rise to the anomalous absorption observed there.
Going back to the ELF hiss, I wrote something down which I thought you said, but which I now don't believe, and wondered if it was true. You said during normal times that you saw more hiss in the dusk sector than the dawn sector? Or was it the... That's what I wrote
in general, we haven't done a thorough study of the local time variation of hiss, but in general you do find you do find plasmaspheric Hiss primarily on the day side of the magnetosphere.
Okay, well that's opposite from what I wrote down. So you do, that's an agreement with Taylor and Gurnett a long time ago showing ELF Hiss peaking on the day side as opposed to the night side.
Yeah, well, some of the emission which is observed in the dawn sector could also be Hiss emissions.
Okay, and you keep calling this plasmaspheric Hiss, and that's because on OGO 5 you see it inside the plasmasphere, but in the ionosphere it's just the opposite. You see the intense Hiss pattern above the plasmasphere, peaking at about 65 or 70 degrees, and that's been seen for years. And how do you explain that?
That isn't true though in the dust sector. You find the Hiss emissions in the dust sector going all the way down to L of about 1.5. And the nature of the emissions seen in the dust sector changed dramatically at about L equals 6, and we then interpret this as being primarily chorus observed outside of the...
Okay, so what you see, ordinarily you would claim to see, as you come across on a dawn-dusk pass, is to see ELF Hiss only on the day side during a normal time and not on the night side, and then as activity...
Well, not only, but primarily.
Primarily, and then as activity builds up, you see it in both places. You see it at the dawn side and the dusk side.
Well, I think the emissions that you see during substorms are primarily chorus.
Well, your two pictures you showed bumps on both sides of the pole, and they look the same. I thought that was your point.
Yeah, well, to interpret the emission as to whether it's Hiss or chorus, you have to look both at the frequency. I didn't show you the power spectrum of the waves. We haven't really got the analog tapes to say definitively what the emission is, but just by looking at the digital spectra, one can look for frequency cutoffs at low frequencies and roughly a few hundred hertz frequency range. And if you see a very sharp frequency cutoff, you can interpret this as Hiss. Chorus doesn't seem to show such a sharp cutoff. But this is very tentative. We're only just beginning to look at this data. I just wanted to point out that it may be very useful to look at such emissions both as a measure of what the source of the plasmaspheric Hiss should be, and also possibly as an indication of what happens to the convection pattern during substorm periods.
I've got a brief comment and a question. The comment is that halfway through your slides, you had two consecutive orbits. I think it was ESRO 1.
Yeah.
And you said that the plasmasphere probably grew from one orbit to the next. But in 1.5 hours, there is no way the plasmasphere can recover with something like 5 degrees. Now, it could be a longitudinal effect, but certainly not a recovery.
Well, you see, the data was taken very close to the bulge region. And,
okay, that's a longitudinal and not a time effect. Then.
But in 1.5 hours, for instance, if you do turn off the electric field, I think you can have co-rotational effects moving the plasma pores around quite considerably.
Oh, okay.
But again, you can't. There's no definitive measure that this was associated with the plasma pore. It's just indicative.
My question is that the only time that I succeeded looking at red arc on OGO 6 and seeing what we can learn about the waves, we saw the red arc and everything seemed to be fine. And we saw what seemed to be electrostatic waves and not electromagnetic waves. Now, admittedly, that was at low altitude. So I'm just wondering if you could care to comment how that fits in with your ion acoustic theory.
Well, electrostatic turbulence of the loss term, post-Rosenbluth loss term cone type, should be generated during the main phase of storms, when the beta of the plasma is high and also when the anisotropy is high, because you're in rapid injection events. But these instabilities get switched off when the density reaches something like 10 particles per cc or so. So it's unlikely that these electrostatic waves would be associated with the plasma pores region. I can't say.
Well, I guess the point is that we saw a beautiful one-to-one correspondence to the red arc position and low frequency electric field.
What was the frequency?
There was an enhancement. These were OGO 6 channels, and Jim Hepner can correct me, but I think they went from 400 to 500 hertz or something like that. There was an enhancement, and we looked at the UCLA magnetic channels, and there was nothing that could be seen within the threshold of detectability. So
on the search coil.
Yeah. So the interpretation is that what was seen at the red arc position was some sort of an electrostatic wave. Now, again, I have to say that was at low altitude, so perhaps there was some sort of wave coupling, but I would have liked to confirm your theory, see electromagnetic waves at the red arc position. And
well, maybe Don Williams will have something to say on that, because on the S-Cube there is an electric field detector.
On one slide, you showed the detached cold plasma region on the sunward side and mentioned that you might get precipitating 100 keV type electrons.
Well, I think more like 500 to an MeV.
Okay,
500 keV to an MeV.
we have brimstrong X-ray data taken at Bird Station at magnetic noon that is exactly in agreement with that. And essentially, we would agree with multi-hundred MeV or KeV electrons and perhaps MeV. And it was during a very quiet period. We saw no other signature in magnetograms or VLF data or micropulse, anything worldwide that we could see at that time. And the problem is that the X-ray bursts that we see are of a duration of about 2 minutes total width. And we have 3 such events that occur spaced 12 to 16 minutes apart.
Mm-hmm. Well, I'd like to see, have a look at the data. The events I showed you there lasted much longer than that. Of course, they lasted for half an hour to 3/4 of an hour.
Concerning the possible association of electromagnetic noise with red arcs, I notice in your talk you seem to concentrate on the fact that noise is generated in the dusk region, but red arcs have been observed to go from dawn to dusk. In fact, they frequently exhibit this property, so that this suggests that if this noise exists, it's got to be in a very broad band of longitude.
I think you were looking at the main phase aspects, but during the recovery phase, presumably when the ionosphere is refilling the region which was depleted of plasma during the storm, the density should build up at all local times, and therefore one would expect the instability to go off at all local times, both on the day side and night side. So we would predict that you should see red arcs during the day side if you had appropriate detectors to measure them.
Could I follow that up and ask what is the present observational situation with regard to?
Well, I hope that Dr. Rees will talk about that. I don't think we should discuss it right now.
I wondered if you have looked when you speak about pitch angle diffusion by ion cyclotron waves of electrons inside the detached plasma region. Is the electron distribution amplifying or damping these waves?
Well, Kelley and I made these calculations about 3 years ago, and the effect on the instability is negligible. They do damp the waves, but insignificantly.
One final comment. Thanks. Referring to Dr. Nagy's comment about the waves observed in the ionosphere associated with red arcs, it's my opinion that we've seen these waves in OE117 too, and even seen them on the day side and correlated them with red arc observations from Washington. And the spectrum and characteristics of the waves is very similar to what Jim Hebner showed earlier in the high latitude regions and so forth. It's my opinion that these waves are electrostatic, but that they're generated in the ionosphere and perhaps just due to a gradient in temperature near the red arc, which causes a drift wave and enhances the electrostatic turbulence. I think they have very little to do with the actual fluctuations causing the precipitation. They're a local effect generated by the heat input into the ionosphere. The spectrum is the same as you see over the poles in that paper by Nagy and Agson and so forth.
You think they're current-driven instabilities?
No, I think perhaps they're just gradient-driven. Grad T drives the instability is the same as grad N.